All right, let's take a look at impulse and 2D elastic collisions. Now, we're not going to go through a full analysis of two-dimensional collisions, although they're very interesting in terms of both elastic and inelastic, but it's a little bit beyond the scope of what we're going to do. But we can handle impulse and a two-dimensional elastic collision type situation. So here we go. What we have is a puck on ice hockey, right? And so sometimes you want to pass to your teammates using the boards. Very effective technique. So here's the puck in the before situation. It has M1, mass 1, and the puck, of course, is the same puck over here. It is also mass 1. So what happens is we're going to give it a little bit of impulse, so it has momentum, and then momentum carries through until the impact with the boards. The boards then send the puck in this direction over here to said teammate. Now, as it happens, when the puck has momentum and approaches the boards, it's doing so with respect to this angle theta over here. And it so happens that when it ricochets off the boards, it does so at the same angle theta on the other side. This is called the angle of incidence, and this is called the angle of reflection. And other things like waves do this as well, like light waves and beams. And so it does happen that this is actually quite true for a puck off the boards. It will ricochet with the same angle on the other side. What we also notice here is that this is V1 naught, this is V1 final, and that they are vectors. They are heading in different directions. This one's heading yay, so I guess you can consider that diagonally up, and this is to the left, and this is diagonally up to the right in the final situation as we look at this from like a bird's eye kind of view. And we're also considering that ice is fairly frictionless, all right? It's got low friction, so we're going to consider this to be frictionless, and we're going to consider this to be perfectly elastic so that there's no kinetic energy lost in this collision with the boards. So what we're going to say is that V1 final is equal to V1 naught. Just the magnitudes. We know that the velocities themselves are not equal. They can't be because they're heading in separate directions because velocity is a vector. But the magnitude, the speed of velocity, will be the same. Okay? And here's our coordinate system. So everything is with respect to, on the drawing over here, up is positive y, and to the right is positive x. So notice that this is coming in at positive y, and it actually starts with negative x. Well, let's take a look at this, and we'll actually look at each part separately, the x and the y momentums. All right. So we've got impulse j equals delta p, the change in momentum, which is momentum final minus momentum original. In the y section here, I've got done up in red, and also the x motion in momentum is done up in green. So let's go with red in the y direction first. So in the y direction, I've got m1 v1 y final minus m1 v1 y naught. Because, you get it, right? This is physics. You know what that means. It's not philosophy where the answer is y to y naught is, or to y is y naught. No, here is y naught, y original, right? So we got impulse y equals m1 v1 final times the cosine of theta. Where does that cosine come from? A little bit of trig. It's a two-dimensional problem. Of course, with an angle, we got trig. So here's our right triangle, and this angle here, as it is displayed, we're going to consider that this side here, the y direction, is related to the adjacent side, which is related to cosine of that angle. And that this side here, if I were to fill this in, this is the opposite side of the triangle, the right triangle, and it's related to the opposite side, meaning the sine, okay? So because I wrote the angle here, the y and x may be switched from what you're used to. You're used to having the x direction be related to cosine, and the y direction related to sine. Well, that's because usually we have the angle down here. Now, you're free to take this angle, subtract it by 90, which is the complementary angle over here, and then use that. It's up to you. But I'm going to stay with what's drawn. I'm going to consider this angle such that over here, the adjacent side is cosine. That's heading in the y direction. That's vertical. So here we go. That's where the cosine comes from. So we've got m1 v1 final cosine theta minus m1 v1 naught cosine theta. All right, the angle's the same from the incident to the reflected. So notice that up here, the speeds are the same. So if the speeds are the same, what I'm going to do is I'm going to substitute that as the magnitude for v1 final. I'm going to substitute in v1 naught. Okay. Now this vector is here because it's indicating it's going in the direction that it was heading in afterwards. All right. So they are different. This is a different direction than that. But because essentially, we're looking at only the x direction. We can then add them together. All right, so we're going to do that. So we got impulse y is m1 v1 naught cosine theta minus m1 v1 naught cosine theta. They're both the same. Two terms that are the same when you subtract together give you 0. Big fat 0. So what does it mean? That means that there's no impulse created by the ricochet off the boards, by that impact, in the vertical direction, in the y direction over here. All right? There's no change in momentum in that direction. It had the same velocity with respect to y as it did when it started, this puck. Here's where the change occurs. It will be in the x direction, okay? So notice that this is heading to the left and that it ricochets to the right, all right? And so that's where we're going to find the impulse. That's where we're going to have the change in momentum, the x direction. So let's take a look. We know that we're coming in negative first, all right? So we got the final direction over here. So we got j, impulse in the x direction is m1 v1 x final. That's the positive direction because it's heading to the right afterwards relative to the horizontal, the x. And then we've got minus from the change in here, m1 and negative v1 x naught. That's because it's heading this way with respect to the x. So we did mention before that this direction here is relative to this angle. We're going to use the sine trig function because of that opposite side of that right triangle. So we got m1 v1 final sine theta minus m1 negative v1 naught sine theta. Angles are the same once again, and so I make the same substitution I did before. The speeds are the same, so we've got m1 v1 naught sine theta minus, and this is negative over here, negative v1 naught sine theta. Well, these two negatives together, multiply together, become positive. So we have two of them. We've got 2 m1 v1 naught sine theta. Done. Okay, so what this says is that the impulse is created only on the x-axis, and it's double the momentum. Okay, so the impulse itself is double momentum times the side of the angle, so it depends on the angle at which you strike. If you strike it head on, that angle is essentially going to be, that's going to be 90 degrees, and this is going to be 0 degrees where it wouldn't hit at all. So it depends on the angle, how much impulse that there is, all right? So that probably makes some sense. So here we go. The impulse is only created on this axis over here with the ricochet. That's the extent of 2D elastic collisions that we'll handle. Right on. More ad, out.